Assalamu alaikum. Good morning, everyone. Please confirm that you're able to hear me.
I can hear you, mister.
Okay, thank you. So we'll continue with lecture 2. We have one thing left, is the source conversion, something that we wanted to do last night, could not. Source conversion, it means if you have a current source, can you actually find the equivalent circuit that will for that current source, but it's a voltage source, or the other way around. So basically you convert the current source into a voltage source, or you convert voltage source into a current source. Now when it says convert, you don't go to the actual source like the source we have in the lab and say, okay, I'm gonna convert it from a voltage source to a current source. But we do this for the sake of analysis. It means we do it on paper. In reality, you can't go to the source and say, I'm going to change a generator that generates voltage to a generator that generates current. Okay, so but we do it for the sake of making the circuit analysis easier. Sometimes when you change or replace a source with another equivalent source, makes the circuit easier to analyze. We will see one example of that. But how to change sources from a source to another source. So voltage source, the equivalent circuit for a voltage source is the voltage source plus the internal impedance in series. Now the reason that we have internal impedance, there is no source that is perfect, okay? So it's not going to be giving you fixed value whatever you connect across it, okay? So when you start loading, the voltage is not going to be exactly the rated voltage. It will drop a little bit because of this voltage, because of this resistance here. So when the current go through, there will be voltage drop across this. So if this is 12 volt, you might have between the terminals of the source, you might have 11.98. Then if you have load that is higher current, maybe it will be 11.96 and stuff like that. So there is a small drop happens in the internal resistance. Now the current source is the same thing. It's not going to be able to give you the current, the exact current here. So if this is 10 ampere, it's not going to give you 10 ampere if you connect it to very high resistance. If you connect it to very high resistance here, let's say 1 mega ohm, it's not going to be 10 ampere for sure. Okay, so what will happen, some of the current will be actually lost inside the source. This is the source. So the source, you know, when you look at the source, say this is a current source, gives you 10 ampere. But when you load it, you see that it's not going to give you 10, it's going to give you something less. Depends on the load anyhow, can give you something very close to 10, but if the impedance increases here or resistance, current will be less. So what happens? This 10 is not coming out. It means some of it will not be lost inside. It will be lost in a parallel resistance here. It's internal resistance. This is inside the source. Okay, so this is equivalent circuit for a current source. This is equivalent circuit for a voltage source. Now, how can I actually convert this into this one? Pretty easy. You just take the resistance from series to parallel. Then the relationship between the voltage here and the current here is just Ohm's law. So if someone says, okay, here's a voltage source. For ohm, 12 volt. Give me a current source that is equivalent to this. Those are the terminals. This is the terminals of the source. You know, in the lab, we have the DC source, for example, like this. It has terminals. Those are the terminals that we're talking about. The one that you use to connect to your circuit. Those are the terminals here. So equivalent circuit for this will be a equivalent current source for this voltage source will be the source with an resistance. I keep saying impedance because in AC it's impedance. This 4 ohm is the same as this 4 ohm, but it's in parallel. Those are the two terminals, still the same two terminals. Now you have current here. Look at the polarity of the voltage, positive here, negative here. So this is going to give me current in this way. So I'm going to put an arrow up. So polarity like that will give me current going up. Polarity reversed is going to give me current going down. But what is the value of the current? 12 divided by 4 give me the current 3 ampere. So these two sources are equivalent to each other. It means if you take this source, you connect it to a circuit, or you take this source, you connect it to the same circuit, you're going to get the same output. It means the same current, the same voltage coming out of the source. Is this okay so far? Questions? No questions? Keep in mind, current source tells you the current in the branch. Voltage source tells you the voltage between the 2 points here, cross the source. This is what they tell you. Okay, here's a question that maybe a source transformation will make the question easier. And I said we're going to show you an example. And this is the example. Here we have two sources. Okay, this is the voltage source. Okay, this is the source, the whole thing. Voltage, the battery and resistor in series. This is the current source. This is the source and a resistor in parallel. So this is equivalent circuit for a current source. Okay. Now the question says find the current I2. So the current going through the R2 here this way. Now might be easy to change this current source between these two terminals into a voltage source, and it's not difficult. It's just you're gonna see the direction of the current is down. It means the polarity is like this for the battery. So we put the battery. What is the value of the equivalent battery? Is just I times R. So 4 times 3 is 12. The resistance is the same. So what I take this source, replace it with a battery, and resistor. The resistor is the same value. The voltage is current times resistance, so it's 12. Why the polarity is like this, positive here, negative here? The direction of the current is going down, so the polarity has to be this way. Now, once I replace between these two terminals, which is now this is A, this is B, I replace this with this one. So what I get this circuit. Now the circuit becomes easier to analyze. Look at the circuit. It's easier than the original one. This is why I said source transformation sometimes makes circuits easier to analyze. Now in this circuit there is one current, which is because there is one loop, and the current, it's what they want, is I2. So the polarity, according to this current, the polarity here is like this, the voltage, and the polarity here is like this. I can use Kirchoff's voltage law, the sum of the voltage in a loop equal to 0. I have 4 voltages here, 4 elements. Each one there is a voltage across it. And I'm going to add those 4 voltages, equate them to 0. Then I solve the equation. I'm going to find this current. And this is what we have in the second slide. This is what we have. This is the polarity of the voltage across the resistors based on the direction of the current. Then I start from a point. If I start from here, I'm going to go all around in the closed loop. So from positive to negative is minus E. Then going from negative to positive, it's a plus the voltage here, plus the voltage here. Then I go here I'm going this way, from positive to negative, so it's negative the voltage across the battery. Then I'm going this way, down, continue. So I'm going from the positive, the negative to the positive, so it's a positive voltage, it's a gain. Again, drop, you go from positive to negative, gain, rise, drop, and rise. I complete the loop. It means sum equal to 0. Now the voltage across the resistor is I times R, so we just plug 3 times I2. We said we named the current in the loop I2. So the current in this loop is 1 current, and it's I2. We have the equation, we can solve for I2, we get the answer. Okay. The voltage here is 3 times the current, 3 ohm times the current. The voltage here is 2 ohm times the current, and the current in the circuit is the same current because it's one loop. There's one branch, no intersection. Is the current going here? It's gonna go here. It's gonna go here. It's gonna go here. It's gonna go down. It's gonna go back and complete and go around again. Any questions about this? If you see it's too difficult, you need to try. If you see it's too easy, do it, and you might find some difficulties. Okay.
Mister?
Yes.
In the calculation, shouldn't it be 3 minus 2 instead of 3 plus 2?
3 minus 2. What do you mean by 3 minus 2?
Because they took the 5 common, right? But shouldn't it be 3 times 2, 3 times I2 minus 2 times, 3 ohms times I2 minus 2 ohms times I2? So shouldn't that be like 1 ohm?
Why?
Because it's 3 minus 2?
Who said it's 3 minus 2?
Because there's a minus sign in front of 2.
Oh, you mean this one here? Oh, you mean this one here?
Yes.
Oh, this is minus sign is a mistake because it was positive here.
Yeah, that's.
Okay, so that's your. I was like, what is 3 minus? Oh, thank you. Okay, it's positive here, so this is actually positive. So it's just a typo when it's just a typo. So that needs to be changed. So let's change it. Okay. Wow, that is a good thing. Thanks for that. I was like looking at the circuit, not here at all, but yes, see, minus E, the voltage, minus E, then a plus here. So why there is minus here? I don't know. Okay. Exercises. I want you to try to do those two exercises. You're going to convert the source you see into another source. Okay. When it says convert, it means you're going to give me the equivalent circuit for the other source. Try it. I'll give you a couple of minutes. They're not difficult to do those things, and you're going to see them in the midterm. Try to figure out the is it DC source or AC source first. Okay. Draw the equivalent circuit that you want and try to find label it. Try to find the information that you need for the equivalent circuit. Okay, so this is for the first one. This is the voltage source. We want to change it into a current source. So current source equivalent circuit is the current source with it is, now this is DC, so the parallel, not impedance, parallel resistance. And those two terminals exactly like those two terminals. Now first thing, this is 1/3 of the work. Now the second part is what is this resistance? The resistance here is this one, 2.2 kilo ohm. 50% of the question is done. Now what is this? Is a current source, but what is the direction of the current? Up or down, decided by the polarity of the battery here. So we look, the battery polarity is like this. This gives a current down. This gives a current in this direction. So this arrow will be going down. Then the last thing, we want to find the value of this current source. So how to do that? We're going to do Ohm's law. I equals E over R. So E is 9 here, and R is 2.2K. And this is around 4.1 milli. So this is 4.1 milliampere. This is the answer. If you just write the equation in numbers, that is a zero thing. That means nothing. This means nothing without drawing the circuit. They give you the equivalent circuit of a voltage source. You give them the equivalent circuit. You give them the equivalent circuit of the current source that they want. Now, the second question, convert the current source into voltage source. I look at it, it's a DC. So the voltage source that is equivalent to this will be a battery. And now the polarity is according to the current. Current is going up, so the polarity is like that. The positive is here and the negative is here. And a resistor is in series. Those are the terminals. 1/3 of the question. This resistance is 3 ohm. And the voltage E here, I'm going to use Ohm's law. Voltage equals to I times R. So 1.5 is the current. This is the current here. And 3 is the resistance. So 4.5 volt. So this is 4.5 volt. And this is the R of the source. Is this okay so far? Any questions? Why we made it from parallel to series? From parallel to series. Because this is the current source equivalent circuit and this is the voltage source equivalent circuit. The question says that. Question says you have a current source. Give me the equivalent circuit for the voltage source that is equivalent to this. This voltage source equivalent circuit is basically the battery and resistance in series. Okay. This is the actual real voltage source. Voltage source is represented by the battery or the voltage and resistor in series. This is a voltage source. Current source is represented by the source for the current, and parallel, this is the current source, the real current source. If it gives you this and says find this, you have to find this. I'm not changing this from series to parallel just for fun. No, I'm finding equivalent circuit to this, but a different source. Now here, what will happen a voltage drop. So in the voltage between this and this, it will drop because of this series. Here, what will happen? A current drop. The current is not going to go completely out, all of it. Some of it will be dropped here. If I leave the resistance in series, there will be no current drop because what goes here goes out if there is no this. Question, how do we determine if it's an AC or DC? First thing, do you see an impedance? That is one. The second thing, do you see angles when it comes to the voltages and currents? That is two. The third thing, you decided from the symbols in the circuit. Okay, this is DC source. AC source is like that. Now there is one case that is a bit confusing. If they give you a source like this, positive and negative, so this may be a bit confusing. Usually I would put this squiggly sign here to show that it's DC. Or you see the voltage 50 with an angle. خلاص, once with an angle, it's not a DC anymore. Is this okay? So impedance is a sign of AC. The source, look at it. If they give you complex numbers, and the symbols of the sources as well, they're different. Most of the time, they're different. Like this, for sure, what we have here is DC. There is no way. Now, this can be a bit confusing, but usually AC, they would put an extra thing to show it's an AC. Okay. Now we'll continue. Here's clearly you can see that this is an AC voltage source, and you want to convert it to AC current source. You can't convert it to a DC current source. Okay, so an AC will stay AC, but instead of the voltage source, current source. Give you 2 minutes to do this. Please do it. So the equivalent current source circuit is going to be the current source and parallel impedance. That is the equivalent circuit for the current source. Now the first thing, that the parallel impedance is basically the same as the series impedance of the voltage source. Now this is the terminal A, so this is the terminal A, because it's equivalent circuit, so the terminal names are the same, the labels are the same. This is exactly, you go to someone and say these two machines are equal, and what is inside is different, but this is the two terminals. This is red, this is black, let's say. This is red, this is black. So the terminals are exactly the same. These two machines do the same job, so I say those are equivalent. What is inside doesn't matter. Let's say for the person who actually wants them for a certain job, if they can do the same job. For you, maybe one of them is a current source, one of them the voltage source. So those are equal, will do the same job, they will have the same terminals. So terminals are the same, okay? Now what is the impedance in parallel? Is this impedance, so it's gonna be the same. I'm gonna put the same thing. 3 ohm, and this is 4 ohm, R, XL, and both together are basically an impedance. Now this is a current going up or down based on the arrow. So, based on the polarity of the voltage here. The arrow will actually be based on what you see here. Plus is up, negative is down. So the current is going to go up. Now it's AC. I'm going to put just another sign to show it's an AC. The value of this current is going to be the voltage divided by the impedance. So it is I here, Ohm's law, voltage divided by the impedance, and here the voltage is 100 angle 0. See, I always use the angles. I don't forget them. Okay, I don't ignore them. I use them unless the question says don't use them. Okay, and this is 3 plus J4. So the impedance here is 3 plus J4. Plug this in your calculator. Actually, someone give me even the answer. Thanks for that.
Sir,
Yes.
can I use like the law of impedance and I make it like one resistor?
Yes, you can combine it. That's fine. You mean
Okay.
you change it into the polar form. For example, this is 5 angle 53.
No. I mean, I solve it by another way. I use Z equal root R2 plus XL power 2.
Okay, under the square root. Then you need the angle as well, which is a tan inverse of this and that. Long way.
So it's okay, yeah.
It's
But it's
okay.
long way.
It is long way. It's really,
Okay.
really long way, and it's not gonna work all the time.
Okay, thank you.
But it is fine. So the angle here is minus 53.1 ampere. So I come here and I say it's 20 minus 53.1 ampere. This is now the equivalent current source. The equivalent current source has to have a current source and a parallel impedance. The voltage source is a voltage source and a series impedance. Now for the voltage source, the series impedance represents the voltage drop that happens in the source when we load it. The parallel impedance for the current source represents the current drop that happens when we load the source. Every source, when you load it, especially with a heavy load, it's not gonna give you the exact current or the rated current for it. It will be a small drop. That drop happens inside the source. How do we represent it? Okay, we want the equivalent circuit that will represent the source. In the voltage drop, we represent it with the series impedance. The current drop, we represent it with the parallel. If you do the opposite, it's not gonna work, because let's say that someone, I say, oh, I'm gonna represent, okay, the drop that happens inside the source with the parallel resistance. This doesn't represent the drop. If this is a 12, you still have 12 here. Nothing drops here. You connect the load, you don't connect the load, it will be always like that. So this is not gonna be equivalent circuit to the source, because in real life, the source, there will be a drop. And I can give you an example for a current source. This is ideal current source, which is not true in real life. Gives you 10 ampere. Okay, says that if there is no drop at all, what will happen? You connect whatever here, the source will give you 10. And that is not going to happen in real life, because you can connect million ohm. Okay, connect million ohm. 10 amps multiplied by 10 million ohms is going to give you 10 million, okay, volt. Then it's really easy to generate 10 million volts. Just bring a source that has 10 amps and connect 1 mega ohm. But that's not going to happen. When you connect 1 mega ohm, most of the current will actually be dropped here inside. It's going to go this. It's not going to come out, because the impedance is very high. Hopefully this makes some sense. Now, question here says, can you show us how to convert it back to the voltage source? Easy. And we'll do it. That's a good question. Okay, so this is the current source. Someone gives you this and says, we want to find that. So what you're gonna do, you're gonna put the voltage source, and now voltage source has a series impedance, not parallel, and which is equal to this. So it's 3 and 4 ohm, 3 ohm. Polarity according to the current, it's going up, so it's positive and negative. The voltage here, 20, the voltage E is 20 angle 53 minus 53.1. This is the current multiplied by the impedance, which is 3 plus J4. When you multiply these two, you're gonna get 100 angle 0. It's gonna be here, 100 angle 0. This is exactly like this. That's okay? Keep going. Any questions? Okay, we'll continue. There are a few questions here, exercises. In those exercises, some of them we will see current sources and voltage sources, okay? And we want to get used to those different sources. We keep one thing in mind, that the current source gives you constant current, the voltage source gives you constant voltage. So what is the current here? 4 ampere, because it's coming here from this source 4. What is the voltage between these 2 points? 24 volt. 24 volt between this point and this point. Now keep in mind, this point and this and all that until here and here, they have the same voltage because there is no drop going this way, same voltage. This point here, it will have the same voltage until here. Then there is a resistor, khalas. Changes, the voltage changes when you have a resistor or a source or something, but if you have nothing, the voltage is the same. So basically this point is 1 point, all these here is 1 point, and all the ones in the top is another point. So the voltage between these 2 points, this and this, is going to be the same as the voltage between these 2 points. The same between these 2 points, because this is connected. No drop here, no voltage drop. When you can see they're connected in parallel. So if someone says, what is the voltage across the current source, Vs, this voltage, you can say it's the same as the voltage across the battery, because they're connected in parallel. This end is connected here and the other one is connected to the other side. The terminal connected here, the other terminal is connected here. So Vs for the current source is basically equal to the voltage E, because they're connected in parallel, 24 volt. S1. Now if I want the current, the voltage cross V, this R1, I know it. So the current I1 actually is the current going in the resistor R1, which is according to Ohm's law, it's the voltage across this resistor divided by the resistance of this resistor. Now the voltage across this resistor between these 2 points, that is the ends of the resistor, is the same as the battery, 24. So it's 24 divided by R1, which is 2. So this is 12 ampere. And this is the second guy. I1 equals to 12 ampere. We got another one. We got this and we got this. Now we can do V3. We can do the divider, or we can find the current. Both are fine. So what is the voltage between these 2 points? Total voltage here, 24. These 2 resistors, 6 and 2, are connected in series, so I can use the voltage divider. Voltage divider, V3. So the voltage across V3 is the resistance 2 divided by the sum of these 2 resistors in series, so 6 plus 2. And the total voltage, 24. So this is 6 volt. So V3 equals to 6 volt, and this is the other thing. You can find the current as well here, which is the voltage divided by the total resistance. Let me draw this here. Okay, this is 24 volt. And there is circuit that side goes that side, but I'm going to look at this side only. These two resistors in series, I can combine them into one resistor, which is 8 ohm. So I can find the current here, which is 3 ampere. 24 volt divided by 8. So the current here is 3 ampere. Take 3 ampere multiplied by 2 ohm will give you 6 volt, the same thing. That's another way to find it. Last thing is IS. There's a current here coming 4. How do I know? Because the current source tells me that there is current in this branch 4. There's current going down here 12, which is this one. It's the voltage divided by the resistance. Now, there is the current going here 3 ampere, and this is 12 ampere. Now, at this intersection, there is 4 coming, 12 leaving. It means there are 8 coming this way, right? I have to have Kirchoff's current law satisfied. The coming currents equals to the leaving currents. The leaving is 12, the coming here is 4. There should be coming 8 from there. So 8 coming and 4 coming, they make the 12. Now this IS will be the current coming to this point. There's 8 going here and 3 going here, so IS should be 11. IS should be 11 ampere. 11 coming, 3 going this way, 8 going this way. At this point, 4 coming, 8 coming, 12 leaving. This satisfies Kirchoff's current law. Any questions? You see the 4 answers, the 4 things that I want in boxes here, in squares. They're not really squares, but kind of more rectangular shape. Repeat what? Okay. The current here is a 12, this current. Voltage divided by the resistance. The current here is 4. Source is telling me that there is 4 going this way. How much is the current here? Okay, 8. Because 8 coming and 4 coming, they will give me 12 leaving. Let's go to this point. There is 3 here going this way. 3 going this way, 8 going this way. How much current should be going this way? See, at this point, there is a 3 leaving and 8 leaving, so 11 leaving. How much should be coming the coming current? There's 8 leaving and 8 leaving, there's 11. So this is IS. Is this okay? Like how to find IS? Now let's to see how to find V3 or VS. Oh, you said VS. I'm gonna delete this. What is the voltage between these 2 points? What is the voltage between these 2 points? Okay, then here's what I'm gonna do. What is the voltage between these 2 points? Same. Well, if I put resistor here, does that change it? No, it doesn't change it. These 2 points are still the same. So this is Vs equals to 24. This value. Is this okay? Now adding something in parallel does not change the voltage. It will change the current. Adding something in series will change the voltage now, like this. Okay, we'll continue. I want you to try this question. So for this network, try to find the unknown currents. Once we read the question, we know what we want. And here we want the unknown currents. It says currents, not one. It means there's more than one. How many unknown currents here? How many currents that we don't know here? Give me answers, please. Okay. Everyone, you can actually share your thoughts, okay? It's good to say what you think is the answer, or because that shows that you're trying to think. Making a mistake is way better than being silent. So we have 4 unknown currents, and their names are I1, I2, I3, and I4. Those are the ones that I have to find according to the question. And I'm gonna write them in a nice box to show that I actually finished the answer at the end. So you should have numbers written here and units to show that you finished the question. Now, what does it say? Use what? Kirchoff's current law. Kirchoff's current law is this: the sum of the coming current to a point, coming to a point, intersection, node sometimes called, equals to the currents they're leaving. Nothing stays at the point. So when I see intersection, this is intersection. This is another one. This is another one. This is another one. This is another one. And this is another one. So how many intersections do I have here? I have 6 intersections. I can make 6 equations. How many equations do I need? 4, because I have 4 unknowns. So I don't need to use all the 6 equations. Now, how many branches do we have in here? Can anyone tell me how many branches do we have? Now, those are the intersections. There's 6. But how many branches do we have? Okay, by definition, the branch is actually the street, okay, the way between two intersections, and the branch should have no intersection in it. Okay, so you go from A to B with no intersections at all, you call this a branch. Until you find an intersection, you stop, then there is a new branch in there. Let's look at how many we have. Let's start from here, this point to this. This is 1. خلاص, from the intersection to the intersection, 1. From here to here, 2. From here to here, 3. Then this way, 4. Then this, 5. This, 6. 7. 8. 9. So 9 intersections, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Did I make any mistake? So I have 9 branches. I'm gonna delete this. Oops, I deleted the nodes as well. Okay. How many small windows do you have? Small loops do we have here? This is one window, small window, not the big windows, the small ones. This is another one. This is a third one. This is a fourth one. So I have 4 small loops, okay, small windows. You can say they have big ones like these 2 together and these 2 together and those 3 together or something, but I'm talking about the simple loops. Here we have 4. So 4 small loops, we call them mesh. Okay, so those are the 4 meshes. 9 branches. And we have 6 nodes in this circuit, which is, we call them nodes, intersections. Okay, it's basically the same thing. Is this okay, those names? This fine? No? How many branches do we have in here? One. Yes, it's 1. There is no intersection at all. You start from here, you can't go anywhere. This is 1 branch. Okay, it's 1 branch. Okay. Now, how many small windows do we have here? 1. Yes. Okay. Now, do we have nodes, intersections? No, we don't. There's no intersections here. Basically, this is 1. What if I add this? How many branches do we have? Give it a try. This is totally fine. Okay, how many intersections do we have? So intersection, this is one, and this is another one, right? Intersection means branches meet together. Now, how many branches do we have? If we go this way, this is one street, one street, one street. You go around, but you have no other options. You reach intersection. Halas, this is one branch. The current going here in this branch will be the same until the intersection. Then there is this in between, and there is this here. So how many branches we have? We have 3 branches. So this is 3 branches. 2 nodes and 2 meshes. Meshes are the small windows. And it's easy to, I can give you an example on here. If the current going here is 5 ampere, just say 5. What is the current here? It's going to be 5. What's the current here? It's going to be 5. For sure it's going to be 5, halas. But once you reach intersection, maybe it's different. Maybe the current here is 2, and the current here is a 3, let's say. So how many different currents? We have 3 different currents because we have 3 different branches. You can't say I can have a current here different, no. Here different, no. Here different, no. It's 3 going around in this branch. Is the idea of the branches and the nodes okay? And meshes, the names at least? This is very important. Okay. Now here's what I'm gonna do. I'm gonna add another thing here. Now give me how many. I'm gonna delete those guys. How many nodes do we have here? Nodes. Forget about my thing here. Forget about my thing. Look at the how many intersections do we have? Four. Thank you. Yes. So what we have this is 1. This is 2. This is a 3. This is 4. So this becomes 4 nodes. How many small windows do we have? Meshes.
3.
That's 3. Now I'm getting good answers. Everyone is almost, this is fine. Now the difficult thing, how many branches do we have? So even myself, I have to actually count. This is not easy. Notice you can look, and so this is 1, this is 2, this is a 3, this is 4, This is 5, and that is 6. So there are actually 6 branches. Remember, branch is between 2 nodes, between 2 intersections. Okay, gonna delete this. See, why I'm saying those 3 things, branches, nodes, and meshes, because the next topic will be, now we did branch analysis. So in a circuit like this, we have to make 6 equations. Then we're gonna do mesh analysis. So we're gonna use 3 equations to solve a circuit like this. So it's easier. And node analysis for nodes, but in node analysis, we're gonna use 3 nodes only. The 4th one is reference. So 3 equations. Go back to the question.
Mister,
Yes.
can you repeat only the nodes, please?
The nodes are the street intersections. Wherever you drive and you find a stop, okay, you're gonna change your intersection. You have an option. Oh wait, because sometimes you stop even in here in the driving. Okay, so whenever you have options to choose an intersection, you can go right or left, you can go up or left or something, okay? That is called intersection. When branches meet, when streets meet, okay? Look here, going from this point, there is no other ways until you reach here. Once you reach here, you can go this way or you can go this way. So this is an intersection. So intersection where branches meets, where streets meet. Intersections. Node is an intersection. I don't know how can I explain it easier than that. This is where this, and this meet. So it's called intersection. This is this, and that meet, called intersection. Now you can't do this as a node, this one here. But if you want to do it, it's okay. It's just an extra node you're adding. There is no point of doing it because you go here, you go here. You don't change your way. You don't have options. The current coming here is the same as the current here. So there is no point of using this as a node. Okay. So the node where actually branches meet, and it is not gonna be less than 3 branches. Okay. You can't have a node and you say 2 branches meet. In this case, it's the same branch. You don't need to put a node at all. But you have like that, then it's a node. So this is a node of 4 branches. This is a node of 3 branches. A node of 5 branches. Okay, a node is the intersection. Is that okay? This
Yes, sir.
is not a node. This is not a node. No. Those are the ones. 3 branches, 4 branches, 5 branches, okay? 2, you're just basically putting a node in one branch. This is the same branch. Even if it looks like that, not straight, but it's still like the straight. There's no difference. This and this, there's no difference. Just bend this guy a little bit, the branch, it's the same branch. We spent so much time on this. Okay, I want you to actually try to solve this question where I'm gonna do the attendance. I did not do the attendance. I'm supposed to do it at least twice today because it's 2 hours. So, okay, do the attendance. I'll do the attendance, do the questions. And your group 4, every day there's someone dropping, someone adding, someone, I don't know what's happening. And there's still some people that I did not see at all, and I'm hoping that they either come to the class very soon or they drop it. And assignment 1 is on D2L. I'm gonna send an email, but it's open right now. So Abdullah Khalid,
Yes, sir.
today is, which day is today? The 4th? Okay, Abdullah, yes. Muhammad Mohsen, if you're around, say yes or write something in the chat. Hassan, so Muhammad Mohsen is not here. Hassan Mahmoud,
Yes, sir.
thank you. Grand,
Yes.
Yazan, Sarah, Abdullah Ali. So
Yes.
Sarah's here, Abdullah is here. Amna Nasser, Maryam Ahmed,
Here, Mister.
so Amna Nasser is not here. Abdullah Ahmed, Yazan, half asleep. Abdullah Ahmed, no. Khalid Ali, no. Asma, you're around. Muhammad Yusuf,
Yes.
thank you. Lean, are you around? Fahad,
Yes, sir.
Amal,
Yes.
Abdullah Hassan,
Yes.
Hazim, Samar,
Yes, sir.
thank you. Ziyad Ali, Awatif, Isam, Manal, Hamad, you're
Ahmed?
around? Yeah, Hamad Ahmed.
Oh, yes. I'm here.
Asia,
Yes.
Umar, Sharif, you're here, yes. Ahmed Ayman,
Yes.
and Abdurrahman, not here. So people who are not here, Muhammad Mohsen, Amna Nasser, Abdullah Ahmed, Khalid Ali.
Mister, you didn't say my name.
Asma is not here. Lean is not here. Hazim is not here. Ziyad is not here. Awatif is not here. And Umar is not here. What is your name?
My name is Ahmed. I just today joined.
Oh, Ahmed.
Ahmed Al-Tayyib Ahmed, yeah.
Ahmed al-Tayyib. Okay, Ahmed. Okay. So we'll continue. So Kirchoff's current law is applied to a node intersection. Okay. Like this intersection where three branches meet here. The sum of the in currents equals to the out currents. So I'm going to look at the currents that are coming to the node. Now, if you look at this node, what currents are coming and what currents are leaving? This is the first equation. What currents are coming, what currents are leaving? If you look, I1 is coming, I2 is coming, and 2 amperes leaving. This one is leaving here. You see it? So this is coming to the node, coming to the node. So N entering, out, leaving. So I1 plus I2 are coming, and the leaving is the 2 ampere. Then we continue. The second node. This is leaving, this branch is leaving, this branch is leaving. 3 branches are connected, the 3 currents are leaving, so nothing is coming. Nothing is entering the node. Leaving is I2 and 7 and 3 ampere. This is the second equation. Then we go to the third node here. Coming is I4, leaving is I3, coming is 7. So the entering current 7 plus I4 and leaving is I3. This is the third equation. Do another one, fourth one, because we need 4 to find those 4 guys. The fourth one, 2 is coming, 2 ampere. Look at the 2 amperes coming, 2 amps. And 4 is leaving, and I4 is leaving. So from here, 2 is the only coming current. And here, I4 and 4. This is the fourth equation. Now let's look at the equations that we can solve right away. 2 and 4 you can actually solve because they have one unknown. So from equation 2, I can say I2 equals to negative 11 ampere. From here, just these are, why did I say 11? 10. 10, right? 7 and 3 is 10. Okay. Then from this one, from 4, I4 equals to negative 2 ampere. And maybe from 1. I know I2 is 10 minus 10, right? From here. So I1 plus minus 10 equals to 2. So I1 equals to 12, right? Then from the equation 3, this is the last equation we did not use. Which is 7 plus I4 is minus 2 equals to I3. And from here, I3 equals to 5 ampere. So this is 5 ampere. I4 negative 2 ampere. I1 is a 12 ampere. And I2 is negative 10 ampere. Look at the calculation. If you there's something that doesn't make sense or something that you think is not okay, let me know. Let me just put the numbers here. So this one we got minus 10, right? And this is 12. So 12 going here, minus 10 means 10 goes that way, 2 goes that way. So that is okay. And here 7 leaving, and 10 is coming. Minus 10 means just the other direction. So that is okay at this node. Here I4 is minus 2. And this is 5. So 7 is coming, 5 is leaving, and minus 2 is coming, which means leaving. So it's okay. So, okay. I think this works in every node. Is this question fine? Yes. Any questions? Okay. No questions? Does that mean it's difficult or easy when people are quiet? Okay, someone has to say it's good or it's okay.
It's good.
Good morning, sir.
Okay. We'll continue. Okay, now we're going to do the voltages. So use Kirchoff's voltage law, and now the voltage law is for the if someone wants this is the answer for the thing before. If someone wants to take a screenshot, if this is the question before, if someone wants to take a screenshot, I think someone needs say someone was typing or something. So take a screenshot and keep it with you. Later you can do it on your own, because I deleted without even tell you. Okay. We will move. Screenshot, by the way, if you're on your laptop, it's just, print screen, or use your phone to take a quick screenshot. Okay, now this question, Kirchhoff's voltage law says sum of the voltages in a loop equal to 0. A loop, we usually use the small loops, the simple ones, easier to use, and they're independent. So find the known voltages. I have V1 here, V3 here, V4 here, and V2. So I have 4 of them. So V1, V2, V3, and V4. Okay, those are the ones that I want to find at the end. I take each loop, I need 4, so I take 4 simple loops. If I go into this one, in this loop, and I'm gonna start from a point, go this way, continue until I finish, go all around. So here, going from positive to negative, it's minus 4 volt. It's negative to me, I'm losing. From positive to negative, I'm losing V3. Then from positive to negative, I'm losing V4 equal to 0. Do the second loop. This is equation, first equation. Now second loop, I'm gonna go this way, 3. Going from negative to positive again, then continue, minus V1. Then I'll continue this way, from negative to positive, plus V3 equal to 0. So this is equation 1 from the first loop, equation 2 from the second loop. Then I'm gonna go here. If I go around this way, plus V4 minus 2 minus 5. So V4 minus 2 minus 5 equal to 0. This is the third equation. Then see, whenever I finish with the loop, I delete it. So I just do the other one. The last one, I'm gonna go this way in this loop. So I'm gonna start here, plus V1, plus V2, plus 2 volt, plus V1, plus V2, plus 2 volt. So it's V1 plus V2 plus 2 volt equal to 0. This is the 4. Now if we quickly look at this third equation, from it V4 equal to 7. Right? 7 to the other side. You go, this is plus, minus, and minus. Then V4, I can plug it in here. I'm going to change the color. So this is 7. So from here, I move 3 to the other side. It is minus 11. So this is minus 11. Then I have V3, plug it here. Minus 11. So I'm going to move this to the other side. 3 minus 11 minus 8. V1 is minus 8. Then V1 is minus 8 here. Minus 8 plus 2 is minus 6. Move them to the other side, 6 volt. You can do this on your own, try it, okay? You can try it and check if you can get the same equations, check if you can get the same numbers. Now I know that this is the answers here, minus 8, 6, minus 11, and 7, so they're correct. You can take a screenshot. Always for me, what I do one loop at a time, then I delete everything, okay, for that loop. So, khalas. Once I do the loop, so I don't get confused, I actually do one loop at a time. Once I finish the loop, I go to another loop and focus on that loop. Because if you try to put too many signs and too many things, you might get confused. Take a screenshot before we do the last question. And by the way, later today, I'm actually going to ask you to have an extra class to compensate for last night. I'm not feeling good about it. Okay, I have to make sure that I actually deliver my hours. No cancellation. So I'm gonna ask you kindly, please come maybe at, I don't know, 12 o'clock, 12:30. I'll send you an email for an extra class to actually continue. So what we lost last night, we will compensate for it today. I think we can do it 12:30. Okay, the last question. This is the branch analysis. When you use the branch analysis, you're going to decide how many branches you have. So we're going to do the steps step by step. So first we find the intersections. This is 1 and this is 1. Branches, we have this is 1 branch, this is 2, this is 3. So we have 3 branches. This is the branch current analysis. First, we know how many branches do we have. 3. That means we're going to have 3 currents. Every branch has a current. Now, done with the first step, I'm going to give every branch a current, and I will name that current. Okay, so let's say that this is a branch. I'm going to say the current is going this way and it's called I1. And this is a branch, I assume it's going to go this way. But it's okay, you can assume anything. That's totally fine. At the end, if you assume something opposite to mine, you're going to have a current with an opposite. Let's say this is this is R3, so I'm going to call it I3. But this is okay, keep it I2, just because. And the current here, I'm going to say it's going to go this way. And it's I2. Those are the 3 currents, I named them. This is a step 2. Now step 3, put the polarity across the resistors. I have 3 resistors. This resistor, the voltage will be like this because the current is going this way. So this is the voltage across the resistor R1. Go to the resistor R2. The polarity will be like this because I assumed the current in this way. You can assume the opposite, you get the same answer at the end. And this is polarity is like this, VR3. Now if I name this I3 and this is I2, it will be less confusing, but it's okay. You could name them even IX, YY, IZ. You can name them whatever. Now I'm gonna make the equation or the equations. I have 3 branches, 3 currents. I need 3 equations. How do I find those equations? From Kirchoff's voltage law and from Kirchoff's current law. So I'm going to look at the small meshes, this loop and this loop. It will give me 2 equations. Look at this loop. If I start from this point, go all around, 4 minus VR1, then minus VR3. Equal to 0. Now, because I'm doing current analysis, branch currents, I'm going to change those equations to their branches. 4. The voltage here is 4 times I1. Then here, the voltage here is 8 times I2. Equal to 0. This is the first equation. Then I'm going to go to the second small mesh, a small loop, this one. If I start from this point, go this way, I'm gonna see this voltage as a positive, going from negative to positive. So it's VR3. And continue. This is as positive as well. I'm going this way. So it's positive VR2, going from negative to positive. Then here, going from positive to negative, it's going to be minus the voltage here, 6 equal to 0. Now I'm going to replace this with the 8 times I2 plus 2 times I2 minus 6 equals to 0. This is the second equation. So this is equation. This is the second one. I found them from the 2 small meshes. Now I need a third equation because I said I need 3 equations. The third equation will be the node, for example, here or here. It's up to you. I have 2 nodes. I can use either one of them. So at this node, the Kirchoff's voltage law says the sum of the voltages is equal to 0, right?
Sir,
Yes.
why you write 8 I3 I2?
What is the voltage according to
Yeah,
Ohm's law?
but yeah, I know, but why we have I2?
Oh, this is sorry, this is I3.
No, sir, make it 2, and for 8, make it 3. So
You want this
it should
3?
be organized. Yeah, that's better.
Okay. So that means this will be here 3, and this will be a 3, right?
Yeah, thank you, sir.
Okay. Okay. Now, the last equation is the equation here. I1 is the coming current. I2 is the coming current equals to I3 is the leaving current. This is coming, and this is a leaving current. This is the third equation. You solve the 3 equations, you find the 3 currents. Now, solving the 3 equations is the best way to do it. Do it with your calculator using matrices. And lots of people actually are able to do it. Even last semester, lots of people do this with their calculators. But in a test, I'm not going to give you 3 equations and so do them manually. No. Okay, the end. I know some of you have a lecture at 10:40, so got a few minutes before you go to your next class. Can we do it tomorrow if it's okay with everyone? My timetable changed and all my classes from Wednesday shifted to Tuesday as well. The thing, it's really difficult to find a time that is free for everyone except 12:30 today. I know you guys are free 12:30 today. Everyone is free 12:30. It's going to be 40 minutes to compensate for the lecture tonight, last night. Please just do this. It's 40 minutes. And I think you can do it. I know your day is going to be long, but that is okay. For the someone said they have class 10:30. You have it 10:40, not 30. So you still have 5 minutes. Okay. So 12:30, I'm going to send an email and to compensate for the lecture last night. And thank you for understanding. Yes. Yes, 12:30 a.m. No, p.m. Like after 2 hours. You go math class, then you pray, then you come back. Okay, thank you, and I'll see you inshallah later. Like, what time do you guys want it? Like 1 o'clock is okay instead of 12:30? 1 o'clock is okay? Hamad, you're saying 1 is fine? We can do it a little bit before 12:30. I know you guys are free between 12:30 to 2 o'clock, I think. No. At night, I'm not going to do anything at night anymore. Last night experience is not good. I did not sleep as well. I don't sleep at nights. I actually did not sleep last night, and I still have class to teach right now and class to teach after. Let's keep it I'll email you 12:45, 12:40 something for 40 minutes, and that's it. And yalla, assalamu alaikum.